Here are three common fuel molecules, things you burn. This one is methane, this one is propane, this one is ethyl alcohol. I'll burn all three for you today. You can see these fuel molecules all have carbons and hydrogens, sometimes with oxygen, sometimes without. Here's another fuel molecule. This is the gasoline molecule. 8 carbons. Here I'm burning natural gas, which is methane, CH4, this molecule. Here I'm burning propane, C3H8. It's this molecule right here. Here I have a fish tank, and inside I'm going to light a fire. Ethyl alcohol in the bowl, bromthiamyl blue in the wells. The mass you can see is 25.63 grams. I'm now going to light the alcohol on fire. You can see the mass is dropping as the fire burns. So here you can see it's getting all foggy, and that's not by chance. This fog is a product of the combustion reaction. The fire made water. That's a paradox that some students find difficult to believe. The fire made water. Here we can see the bromthiamyl blue has changed color. This one here is almost all yellow. This one you can see the blue is in there in the middle, but there's yellow on the surface or around the blue. These are still mostly blue on the bottom. So bromthiamyl blue will turn colors when you add carbon dioxide. Bromthiamyl blue will change colors. So watch this. So I was just breathing my carbon dioxide through this pipette into the bromthiamyl blue, and you see a nice color change from blue to yellow. So here we have evidence of carbon dioxide, and the fog is evidence of water produced, H2O vapor. So a combustion reaction starts with a fuel that combines with oxygen to produce carbon dioxide gas and water vapor.
Now that you've seen gases burn in real life, I'm going to show you how to fill out the online lesson. So open up the online lesson number 9, Combustion Reactions. The first thing that you'll need to do is the pretest. So here's the link to the pretest. Go ahead and do that first. After this, you'll complete the first page using video instruction here with me. Then you'll do the practice problems on page 2, and then the post-test to demonstrate your skill is due Wednesday at midnight. Let's go ahead and look at number 1. A typical propane canister used for camping contains 450 grams of propane. So here's a propane tank. You saw it burn in a lantern, and sometimes they're used in grills and camping stoves and all that stuff. And when you see propane light on fire, this is what's happening chemically. Propane gas, 3CH8, combines with oxygen and an ignition, so an input of energy, will produce CO2 gas and water. First, we need to balance our chemical equation. To balance this chemical equation, we will need to use coefficients to make the number of atoms on the reactant side equal to the number of atoms on the product side. You can see I have the molecules drawn out here. Here's propane, oxygen, which is O2, CO2, and H2O. You can see here that I've got 1, 2, 3 carbons on the reactant side, and on the product side I only have 1 carbon between all of my molecules, meaning these are unbalanced. So let's start by first balancing our carbons. Since there are 3 carbons on the reactant side, I will also need 3 carbons on the product side. The only molecule that has carbon in it is CO2, so I will need 3 of those molecules. So 3 will be the coefficient. That means I have 3 of this entire molecule, 2 and 3. So we can now see that my carbons are balanced. I've got 3 carbons here, 1, 2, 3, and 3 carbons on the reactant side. Next, I'm going to balance the hydrogens. On the reactant side, I've got 8 hydrogens, but on the product side, I only have 2. Meaning in order to make this 8, I'll need a few more of those molecules. Since each water molecule contains 2 hydrogens, and when you're balancing, you can only add entire molecules, I'll need 4 water molecules to make that 8 hydrogens. So you can see here I've added in 4 water molecules, bringing our total amount of hydrogen to 8. Now my hydrogens are balanced. The last thing that I need to balance is my oxygen. Because my oxygen exists in 2 different places, here in CO2 and here in H2O, I'll need to add the total amount of oxygen together in order to decide how many of these O2 molecules I start with. So in my CO2 I've got 1, 2, 3, 4, 5, 6 oxygens, and on my water, if I add it to my 6 here, I've got 7, 8, 9, 10. On the product side, because atoms cannot be created nor destroyed, I have to input 10 oxygen molecules. However, because oxygen is diatomic, it exists in a pair. So therefore, I will need 5 oxygen molecules. So in the end, the balanced reaction looks like this. 1 C3H8, 5 O2 molecules, 3 CO2s, and 4 H2Os. So I can make a table of my totals to make sure that they're equal. Carbon on this side I've got 3, hydrogen I have 8, oxygen I have 10, and over here I've got 3 carbons, 1, 2, 3. I've got 8 hydrogens, and oxygen I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can see that they are same on each side. So this is a balanced chemical equation. So now that you've seen how to balance it, I'm going to write the numbers in here. 1 propane plus 5 oxygens produces 3 CO2s and 4 water molecules. The question is then asking you to calculate how many moles of CO2 are produced when 450 grams of propane are burned. We can use information from our balanced chemical equation to figure out the answer to this question. The chemical equation is showing us that 1 mole of propane produces 3 moles of CO2. We use the coefficients as our molar ratio. Therefore, if we can convert 450 grams of propane into moles, we can use this 1:3 ratio to figure out how many moles of CO2 are produced. In order to calculate how many moles of propane we have, we'll need to use the molar mass, or the molecular weight. If you scroll to the top here, you see I have carbon and hydrogen. And in the box here, it says 1 mole of C3H8 is equal to a certain amount of grams. And this is something we can calculate using the chemical formula. So for carbon, I've got 3 of them, because it has a little 3 here. And that little 3 is telling me that I've got 3 carbons. So 3 carbons times the weight of 1 carbon, which is 12, gives us a total weight of 36 for carbon. And for hydrogen, we have 8 hydrogens based on the chemical formula. H8 tells us we have 8 of those, times 1 gram gets us a total of 8. And if we add those together, 36 plus 8, we will end up with 44 grams. That goes here, 44. 1 mole of C3H8 is 44 grams. That's how much it weighs. So you also see it written here, 44 grams per 1 mole. We can now use that information in our calculation. 450 grams of propane. Now we need to convert that into moles. So we put 1 mole on top, 1 mole of C3H8 is equal to 44 grams of C3H8. And if we do that calculation, which is 450 divided by 44, you'll get 10.2 moles of C3H8. Now that we're in moles, we can use the molar ratio 1 to 3 to calculate how many moles of CO2 we produce from 10.2 moles. So there's 3 moles of CO2 for every 1 mole of C3H8. And 10.2 times 3 is 30.6. So 450 grams of propane produces 30.6 moles. So in this problem, we use the coefficients from the balanced chemical equation, which is our molar ratio, with our molar mass to calculate how many moles of C3H8 we had. And when they burned, using the mole ratio, we use that to figure out how many moles of CO2 were produced. Now that we have completed number 2, we can look at number 3, which uses some of the same principles as we were looking at before. So the question is asking if Lars Gutfernuten decides to use a propane-fueled camp stove to cook some artichokes in an airtight room that has a pressure of 1, and the volume of the room is 8,000 liters, what fraction of the room's oxygen will be consumed when Lars burns the 450 grams of propane? What the question is asking you to do is figure out how many moles of oxygen are being used when we burn 450 grams of propane. Then the next step is to figure out what fraction of the room's oxygen is being consumed in this reaction. So the first thing that we can do is use the chemical equation and our mole-to-mole ratio to figure out how many moles of oxygen are required for 450 grams of propane. So much like we did in problem number 2, we'll need to do this first part where we convert 450 grams of propane into moles, because the question is asking about 450 grams of propane. So we already have the answer, 10.2 moles of propane. That's how many moles of propane 450 grams is. Then we can use the mole-to-mole ratio, 1 mole to 5 moles, to figure out how many moles of oxygen are required for 10.2 moles of propane. It's a 5-to-1 ratio, so 5 moles of O2 per 1 mole of C3H8. 10.2 times 5 equals 51 moles of O2. Now that we figured out we need 51 moles of oxygen to burn 10.2 moles of propane, we have to figure out how much air is in the room in moles. We'll do that using PV equals nRT. So let's fill out our table on the side. Pressure is 1 atm. The volume of the room is 8,000 liters. N is what we are looking for. R is always 0.082, that's a constant. T is temperature, 295 Kelvin. That's room temperature, about 72 degrees Fahrenheit. So now let's go ahead and fill in PV equals nRT. 1 atm times 8,000 liters equals N, which is what we're looking for, times 0.082 times 295 Kelvin. Now we do some algebra. 1 times 8,000 and then 0.082 times 295 times N. So we leave our N variable. 8,000 equals 24N. And if we divide both sides by 24, 8,000 divided by 24, N equals 333 moles. There are 333 moles of gas in the 8,000 liter room. Using this information, we can now finish the problem. If we assume the room is 100% oxygen, then the reaction uses 51 moles of oxygen out of 333 moles total oxygen. So if the room is 100% oxygen, I'm saying I've used 51 of the 333. So to get a percentage or fraction, 51 divided by 333 times 100 is 15% of the oxygen is consumed. However, what you may be thinking to yourself is, air is not 100% oxygen. In reality, air is only 20% oxygen. So if the air is only 20% oxygen, we can first start with that. 20% of 333 is 67 moles of oxygen. Meaning out of the 333 moles of air that we have in the room, 67 of those are oxygen. Meaning, in reality, if we use up 51 moles of oxygen for our reaction, out of the 67 that are in the room, we're really using up 76% of the oxygen, which is a lot of oxygen to consume in this reaction. So you better open a door soon so that you don't pass out. All right, so now you can see here that we have used a balanced combustion reaction to figure out the amount of products that we can make from it, the amount of reactants that are required, and we've used our gas law, and we've used our ideal gas law to take these problems one step further, knowing that we can use moles of gas here with our chemical equation to do more complex problems. You now should have enough skill to complete the practice problems on page 2.